So within the molecule, and I'll draw the outline of the molecule for you. Within that molecule, those things are all held together by shared electrons. But what makes that molecule stick to the next molecule? Why don't they just break up into individual molecules there on your desk in a little pile of grit? Well, you might think that the answer is something that I'm going to put up on the board. Intermolecular forces. So if anybody else gets confused about inter and intra, anybody else struggle with that? Inter-county league, intra-county league, blah. Interstate highways go from one state to another. They go between two different states. An intra-state highway, if we draw the state of Ohio, an intrastate highway would never leave the state. Okay? So intermolecular forces are forces that connect different molecules. And they're just a force of attraction. So the best proxy for intermolecular forces is boiling point. The stronger the forces of attraction between each of the molecules in a substance, the higher the boiling point tends to be. Okay? Because when you heat something, when you add energy, what you're doing is breaking the bonds between the individual parts, and once they're in a gaseous state, there are no forces of attraction. So that's what you're doing. In general, within two molecules, so let's take, oh no, that's a terrible example. We'll just make these little blobs. The forces of attraction between two molecules are not as strong as the forces of attraction inside the molecule. So they're not as strong as the forces that hold all of those carbons and hydrogens together. They're weaker than that. They're not as strong as the bonds that hold ionic compounds together, the ionic bonds. And you did a lab where you had a really good proxy for that, remember? What was the difference between the ionic compounds and the molecular compounds in terms of, and there we just melted them, we didn't even boil them, but in terms of melting point? Which ones could you get to melt with a candle? The molecular compounds, the sugar, the phenylsalicylate. Things like sodium chloride don't melt at those kind of temperatures. They are very high temperature melters. So these bonds are weaker than those. And the other one that's important to note, the bonds between two atoms in a chunk of metal are much stronger than your general intermolecular forces. So the easy proxy for this is, could you vaporize sugar in this room with a Bunsen burner? Yeah. Could you melt steel in this room with a Bunsen burner? No. So that's your proxy, is boiling point, and I just used melting point, but can you vaporize steel? Yeah, you can. Not at a temperature you're going to achieve in here. But certainly any substance can be a gas, liquid, or solid. Okay, let's talk about, there are three big categories of intermolecular forces that we're going to look at. The first two are the ones that are more important. The third one is kind of a toss-off. We don't stress that one. Okay, so the first one, it's actually called a dipole force, and it's molecular polarity. So, do you remember polar covalent bonds? What does a polar covalent bond create? A molecule that has what? Creates a molecule that has, so we end up with an electron cloud being held more closely to one atom. That creates a region of partial negative charge. The other area by default has a region of partial positive charge. And so within a grouping of these molecules then, you have these forces of attraction. Now dipole forces, it's important to know this. They don't act over long distances. So if you remember when we had our ions, every ion in there is pulling on every other ion. It's forces running in all directions. With metals, there are forces running in all directions because you've got little nuclei and a sea of electrons. With these things, the dipole forces are only acting on the thing that is immediately adjacent to them. It doesn't act at a long distance. So these are not terribly strong. The next kind of intermolecular force is what's called hydrogen bonding. As you might guess, this only happens in things that have hydrogen. Yeah. And water is a great example for this one. So we have water. And we know that several things are true here. One, we know that the oxygen in water has two unshared pairs. And the other thing we know is, what do we know about oxygen in terms of this compound? It's an electron hog. So a lot of the electron cloud, and this is my electron cloud, ends up further down on this part of the molecule. Well, what happens is within a bunch of water, these little hydrogens, which are really just protons, end up being attracted, they end up being attracted to the unshared pairs of the other waters. Okay? So they end up being attracted to those unshared pairs. There are two things this does. It drives up the boiling point because you've got a force of attraction between the molecules. You have to get energy to overcome that before you can take them from being a liquid to being a gas, where they're just flying free all over the place. Stronger the forces of attraction, the higher the boiling point. The other thing this does, and you have this to thank for all kinds of things, is it creates what we know as surface tension. So let me give you there's our little demo space. So if we have a glass of water, on the surface of that water, every little water molecule, is strongly attracted to the water molecule next to it. And there are two things. Water's polar, so it's got those dipole-dipole attractions, but more importantly, it's got hydrogen bonding. This is a much bigger deal for water. And because of that, what you get is this like interlocked network. This is looking down on the glass. This little interlocked network. It's terrible. Oh, no, that's not what I wanted. No, that didn't work either. Okay, so anyway, looking down on it, you get all of these interlocked little molecules where they are locked in step and they don't want to move. This is why you can have a little tiny insect that seems to be able to walk on water. What are those called? Water striders, because they stride on the water. And they have little tiny discs on their feet, and they ride on surface tension. This is why you can float a piece of paper on the surface of water. If you're really talented, you can float a needle on the surface of water. Yeah, Try it at home. It's riding on surface tension. And what it's really riding on is these little forces of attraction between all of the water molecules. So it creates surface tension. Okay, the last intermolecular force we're going to talk about is the least important. So these are London dispersion forces, and they're very weak. These are seen between nonpolar molecules. So in polar molecules, these are so weak we would never see them. Noble gases can even have London dispersion forces. So imagine, if you would be so kind, an atom. Let's even make it an atom of neon. I'll move it over a little bit. Now, it's got that big fuzzy electron cloud all around it, right? Cotton candy wrapped around a tennis ball. At any given point, all of the electrons that are present in that neon, could be any place. That doesn't work. They can be anywhere, because remember, the orbitals are just the region of high probability. So, it is entirely possible that at some point, a bunch of them end up in the same neighborhood. These things are moving very, very fast. At the billionth of a second, where they all end up in the same neighborhood on one side, what you have now is a region of partial charge. It pops into existence. It's attracted to a region of positive charge on something else. And so these little forces of attraction pop, happen, and then they keep moving. They pop, happen, and they keep moving. These are not consistent. These are brief. They're weak because they pop in and out. So this is the textbook definition: intermolecular attractions resulting from constant motion of electrons and the creation of instantaneous dipoles. So what that means is, for a billionth of a second, you have a dipole and then it's gone. And then you have a dipole over here and then it's gone. So while that's happening, you get forces of attraction. These are the least important ones to know. I do want you to know more about the hydrogen bonding and molecular polarity. We mentioned this, but I want to just make sure. If you had two substances that were alike in most other ways, but one is polar, so that'll be substance A, and one is non-polar, that'll be substance B. Do not yell this out, jot it down. Which one would you predict would have the higher boiling point? Jot it down and then compare notes with a friend. And then after this, you can get rid of your sugar. Okay, talk it over with a friend now. If you had a polar substance and a nonpolar substance, which one would have the higher boiling point? Pardon? Which one would have the higher boiling point? Okay, so how many of you agreed with what your neighbor or cohort or friend said? Okay, what did you say? The nonpolar would have the higher. Really? Okay, so who here said polar? Who said nonpolar? Okay. Ella, convince Rachel that you're right. I'll pause. If you are a polar compound, what does that mean? It means you have regions of partial charge. It means you have dipole-dipole forces. If you're a nonpolar compound, how are your forces? Do you have anything similar in terms of intermolecular forces and attraction? Remember, the stronger the forces of attraction between the molecules, the boiling point? Higher. So, if you have something that has dipole-dipole forces versus something that doesn't, so this one would have dipole forces, this one does not have any dipole forces. Oops. Which one's going to have the higher boiling point? Polar compounds tend to have slightly higher boiling points than things that are similar in other ways but are nonpolar, because those forces, those dipole-dipole forces, pull the molecules together and make it harder to move them apart. You have to have more energy to overcome that. Water and alcohol are a great example. Water's got both dipole-dipole forces and hydrogen bonding, so it's got two things that up its boiling point. Alcohol, rubbing alcohol. Which evaporates faster, rubbing alcohol or water? Rubbing alcohol. It is nonpolar. Because it's nonpolar, it's got a much lower boiling point. So it'll evaporate really fast at room temperature. Water takes a lot longer. Water takes a higher temperature. Okay, with that, hydrogen bonding, London dispersion forces, that is it, folks. So here's the agenda. You've got the rest of the time to work on the labs. They're due tomorrow. Your test is Friday. Because these labs are functioning in lieu of homework for the latter part of the chapter, what we're going to do tomorrow is we will grade and go over them as a group so that we know that you're all on the same page. They will be due in the second period that we meet tomorrow. So they'll be due 7th. You'll have the first period to work on them together, take whatever time you need. I would also strongly advise that if you, and it's nice in here because we've got some pretty small lab groups and that really is helpful, but if you felt at any point in the lab like, I'm not the one who's coming up with this stuff, I'm getting dragged along, I don't really get it on my own, I would encourage you, I can get you a blank copy of the lab, you can redo some Lewis structures, redo some constructions, just as a study technique. Because, and the other part of it is, I don't know how many times I've done the Lewis structure for nitrogen. Sometimes I'll still do it and then I look at it and go, how does that work? So, you know, redo some of those Lewis structures. There will obviously be a fair number of Lewis structures on your test, so you want to make sure that you're comfortable with those. Questions, comments, concerns? Okay, you got time?